Okay, in this presentation we're going to look at continuous random variables. So what we have here is a PDF, which is a probability density function in terms of y, so f of y. And it's defined as follows: k times y plus y cubed, where y is between 0 and 2, okay, and 0 elsewhere. So specifically, this is the bit we are interested in up here. And it's important to note that we are going to be dealing with integrals here. So this is the lower limit and the upper limit. 0 is the lower limit and 2 is the upper limit. Okay. Now, the first thing we're asked to do is evaluate k. So k has to take some number. Okay. So what we're going to do is use this little equation here. Okay. This is the integral of the PDF. And that has to equal to 1 between the upper limit and the lower limit, or sorry, the lower limit and the upper limit, okay? U for upper limit, which is 2, okay? And L for lower limit, which is 0, okay? Now, I just wrote it in terms of x there in general sense, so this is not specifically in terms of y, it's more like the formula we're going to use, okay? So let's just progress things along there. This is to sort of just get us going, okay? So the upper limit is 2, the lower limit is 0. We can disregard the other part, the elsewhere part, and just concentrate on that. That's all we need. And the integral of f of y with respect to y is 1. So the integral, the integral of f of y, we integrate the PDF, essentially, okay? Now that has to equal to 1. So let's just actually work it out. This becomes a straightforward definite integral calculation, okay? So I'm going to sort of skip through it very quickly, okay? Y, there we have it. Y becomes, when you integrate that, y squared over 2. Y cubed becomes y to the power of 4 over 4. The limits of the definite integral are 0 and 2, okay? Now just be careful with this actually. I sort of deliberately put this part in, 0 plus 0, because you might actually automatically put in 0 and 0 there when you see the lower limit of your integral as 0. But just be careful, because sometimes that does not work out to be the case. Double check it. It's a nasty little trap, okay? But in this case it's 0 and 0, okay? So I'll just evaluate the full thing. So 2 times, when we let y equal to 2, 2 squared over 2 is 2. When we let y equal to 2, y to the power of 4 is 16. 16 divided by 4 is 4. So we have 2 plus 6. 0, 0, and when we let y equal 0 there, it's 0. So in this case, 0 and 0. So, but you just have to double check, okay? So when we work that out, we would add that up to be 6 minus 0, which is 6. So 6 times k is equal to 1. Therefore, k is equal to 1/6. Now, the next part of it is as follows here. I'm just going to sort of progress here a little bit more, okay? So the next thing we have to do is compute the CDF, the cumulative distribution function, okay? Capital F of y. So this is capital F of y, and sometimes I put in a little capital Y subscript there, okay? So I should have been consistent with the last time, but I didn't. But we'll keep going anyway, okay? But just to note, capital Y is a cumulative distribution function. In the last one, I used small y, which is the PDF, the probability density function. Two completely different things. Okay? So this is the CDF, and this is f of y of y, fy of y, and that's the probability of y, that's the variable name, being less than some particular value of y. Okay? Like, capital Y is the variable name, lowercase y is just some specific value that it can take. And again, what we're going to do here is use the same sort of formula that we've used before. So 0 here is the lower limit. Now, y stands for some value between 0 and 2. Okay? So y is any possible value between 0 and 2. Okay? Now, what I'm going to do here is when you actually use these out, you use a different letter or symbol from y when you're trying to calculate the PDF, or the cumulative distribution function. Now, that'll become clear shortly because we're going to use y when we evaluate this, which is the reason we do it. So we just use u as anything that is not y, okay? So it just actually, what we do here is just like, from our PDF, just instead of using y, we just use u instead, and then we can put y into the integral up here, and then y comes back into it, okay? So it's just essentially a sort of notation substitution technique to stop things getting confusing, okay? Anything as long as it's not y, because we're going to use y when we evaluate the definite integral. Anyway, I'm rambling now. So this is a very simple, straightforward definite integral, okay? Just like what we've done before, 1 over 6 times u squared over 2 plus u to the power 4 over 4, evaluated between 0 and y. Okay, so when we evaluate it at y, then we get our definite, our CDF. Okay, so it's 1/6 over y squared over 2 plus y to the power 4 over 4. Working that out a little bit more, you can simplify it as follows. Now this is important, this bit. This is the A1, well, this is to be very formal, okay? This is the full CDF here, okay? Now, you have to state fully that it's 0 when y is less than or equal to 0, and 1 when y is greater than or equal to 2, okay? So actually, I'm being a little bit haphazard there. I've actually accidentally used less than or equal to up here, and used less than and here, but just as long as you're consistent. I'm actually not being consistent there. Really, I should use less than there as well, just to be consistent. It doesn't really matter so much. Now, as long as you're consistent, it doesn't really matter. So 0 where y is less than 0, that's our CDF there between 0 and 2, and 1 where y is greater than or equal to 2. So that's the full answer there, okay? That's your A1 answer there, okay? Well, actually, probably a little bit more again. You can just put in a few more things there. But that actually gives us the full thing. So essentially what I'm saying is, don't stop here. Just write it out fully, okay? Go the whole hog. Okay. So the next part is... So the third part of this is as follows. So what we have to do here is evaluate the cumulative distribution function. Essentially what we have to do is find this interval probability here for y, okay? Where y is between half and 3 over 2. So essentially what we're going to use is our CDF, which we've just evaluated there just a few moments ago. And f of y, let's actually put that in here just to be consistent. Now, is essentially this is an interval rule, okay, for computing an interval, a probability of an interval. So the upper limit minus the lower limit, the CDFs are the difference between the two, okay? So essentially what we're just going to use here is essentially the calculation with the formula that we've just used previously. We're going to evaluate f of 3 over 2, okay, working it out. Now, I could have evaluated it a little bit more, and in fact I actually did, and I just, if you just sort of see that, I might have actually just tip-X some stuff out there, but I just decided to leave it as is, okay, not go too far with it. Okay, so when I evaluate it as f of 3 over 2, I end up with 9 over 48 plus 9 plus 8 over 8, which is 17 over 8, okay? Now, when I evaluate the CDF for 1 over 2, let's just straighten that up. I get something similar here, 1 over 48 plus 1 plus 8 over 8. Okay, so we essentially it just makes it sets it up nicely to cancel out when we subtract one from the other. So the difference between the two is our interval probability. Okay, so f of 3 over 2, the CDF of f of 3 over 2, 9 over 48 times 17 over 8. And for 1 over 2, the CDF is 1 over 48 times 9 over 8. Working that out, essentially what I get is 16 over 48 times 8, 9 times 16 over 48 times 8. Simplify that down, I get 9 over 24. Okay, so that part of it is actually just a bit of number crunching, and just essentially the key thing that you have to remember there, okay, is just how to calculate an interval probability, the CDF of the upper limit minus the CDF of the lower limit. That's all you need to do. Okay, so the last part of this I have to find. I'll pause it. I've just unpaused it there. I just had to find the last document. So the question actually, the last question is evaluate the variance of y. Okay. Now, essentially what we're going to do here is to evaluate the variance of y. We use this formula here, the expected value of y squared minus the expected value of y to be squared, okay? This is a very standard formula that you use in probability theory, so it's one you should have learned off by heart. So there's two parts to this. Essentially what we have to do is evaluate the expected value of y, e of y, okay? And the general formula for that is, again, something you should also know. The expected value of y is the definite integral between the upper limit and the lower limit, or the lower limit and the upper limit, pointing in the opposite, of y times f of y, that's the PDF, times dy, okay? Or in respect to dy. So essentially what we have here is 1 over 6, which is our k function that we found earlier on. And so this is our PDF here, our probability density function, y plus y cubed. And what we're going to do is multiply that by y and then calculate the definite integral there. So this is a definite integral again, so I'll just sort of boost that up there, okay? E of y equals 1/6. So y times y, sorry, let's just bring that down there again. Y times y is y squared. When we integrate that, y cubed over 3. Y times y cubed, that's y over 4. When we integrate that, we get y to the power 5 over 5. And we evaluate between the upper and lower limits of 0 and 2. Okay, so when we evaluate it at 2, we get 8 over 3 plus 32 over 5. And when we evaluate it at 0, we get 0 plus 0. Again, always check that. Let's just rotate that in a second. Always check that, okay, times 1/6. So essentially what we have here is 1 over 6 times 40 plus 96 over 15, which you can evaluate as 68 over 45, or just go the whole hog and call it 1.511. Okay, so that's the first part done. The second part is evaluate the y squared, the expected value of y squared. Pretty much the same sort of calculation. The only thing we're going to be doing differently in this case is that we are going to use the y squared rather than y, okay? Do the same sort of calculation again, and let's just bring up the next page. Oops, hang on a second, there we go. So finally, there we go again. E of y squared equals 1/6 of y cubed plus y to the power of 5 dy. So y squared times y is y cubed. When we integrate that, y over 4. Y to the power of 5, integrate that, y to the 6 over 6. It's a definite integral again. What we get is 22 over 9, which is 2.555. Okay. And so essentially when we evaluate, put these values in, the expected value of y squared, 2.555, and the expected value of y, which is 1.511, square that, just separate, calculate out the difference between the two, and we should get an answer of 0.161. So that is the variance of y, and that's all of our parts done on this continuous random variables question. So we'll leave it there. 13 minutes is quite long.